visiting us from far out of town. And he's going to be talking about places that are even more far out. So, all right, are we ready to roll? All right, it's rolling? Okay. Dr. Lewis Irwin, a native West Texan, received a BA in chemistry from Texas Tech, a PhD in biochemistry and physiology from the University of Kansas. He has served on the staffs at the Shriver Center for Mental Retardation in Waltham, Massachusetts, and the Neurosciences Research Program of MIT, on faculties at the College of Pharmaceutical Sciences at Columbia and the Wayne State University School of Medicine. He has been chair of biology at Simmons College in Boston and the University of Texas at El Paso. Trained as a physiologist, his early and continuing interest in neuroscience and evolutionary biology has led to over 60 publications in those fields, including 2 books, Scotophobin and the Evolutionary Imperative. In the last 2 decades, he has added astrobiology as a natural extension of his earlier interests. And that has led to 20 publications, including 2 books, Life in the Universe and Cosmic Biology. Currently, he is a Solar System Ambassador for the NASA JPL lab and Professor Emeritus of Biological Sciences at the University of Texas, El Paso. I give you Dr. Lewis Irwin.
Thank you, Jonathan, for that kind introduction. It's a real honor to be here to speak at the Astronomical Society, the Warren Astronomical Society. I thank you and your colleagues for the invitation. I thank Jerry Mitchell for helping to engineer it, and also for the artwork that forms the backdrop of my title page. Nearly everything I talk about this evening is going to be from these 2 books, written with my longtime collaborator, Dr. Dirk Schultz-Markuch. Life in the Universe just came out in its 3rd edition this year, so it's quite current. It's the more technical of the 2 volumes. Cosmic Biology is designed more for a general reader. So when I say I tonight, more often I really mean we, Dirk and me. On December 15, 1970, the Soviet probe Venera 7 radioed good news and bad news back to Earth. The good news was that it had landed functionally intact on the surface of Venus, the first man-made object to land successfully on another planet. The bad news was that at an atmospheric pressure 90 times greater than that on Earth and a temperature hot enough to melt lead, it probably wasn't going to last long. Indeed, 23 minutes after it started transmitting, it stopped transmitting on its way, presumably, to a crushed pool of molten metal. It's difficult to imagine a more hellish environment and a more unlikely habitat for life in our solar system. And yet there are some who believe that Venus might offer the best prospect in the short term for discovering life on another planet. Before I explain why that is the case,
move his microphone just a little bit to the side.
I'd like to clarify some concepts and define some terms for the rest of the presentation this evening. First of all, I'm going to be talking about organic life tonight. I'm not talking...
There you go. So it doesn't...
Is that better?
Yeah.
Thank you. I'm not going to be talking about synthetic life or electronic life or mechanical life or virtual life. I'm talking about organic life, which is defined as enclosed systems of chemical interactions, responsive to environmental changes, using energy input to maintain a lower level of entropy than its surroundings, and critically capable of, or the product of, near identical replication from parental forms using raw environmental constituents. There are 3 requirements for organic life. One is metabolic complexity, molecules capable of carrying the large amount of energy necessary to properly coordinate the biological processes of living systems. Liquid and energy from the environment. Now, energy, if it's in the form of light, as plants utilize it, are called phototrophs, and energy that is derived from chemical reactions are called chemotrophs. Another term that's useful is autotrophy. An autotroph is an organism that manufactures its own food, as plants do. They use light energy to manufacture their own high-energy organic compounds, whereas organisms that derive their nutrients from organic compounds already with high energy are called heterotrophs. They can be chemotrophs, but more often they're organisms that derive their energy by consuming other living organisms. Now I'm going to be talking about ecosystems tonight because the abstract concept of life isn't very useful when we're looking for evidence of actual organisms. So an ecosystem to a biologist has at least 3 components. First is energy. Second is the habitat itself, in this case a marine habitat. And thirdly is a network of organisms through which energy flows in a complex trajectory. Now we can formalize the flow of energy by identifying, first of all, those organisms that collect the energy, the raw energy from the environment. They are producers. Then organisms that consume producers are primary consumers. And those who eat the primary consumers are secondary consumers. And then finally, at the top of the food web are tertiary, or in some cases, quaternary consumers. So those are the kind of the formal elements of ecosystem, and I'm going to be focusing on ecosystem the rest of the way. So now, let's get back to Venus, the brightest body in the late evening sky and early morning sky, other than the moon. It's very bright because it has a very thick layer of clouds that reflect most of the light that impinges upon them. Now, if we, or when we became able to peer beneath the clouds, we saw that in fact the surface of Venus is quite heterogeneous. This is color-coded for elevation, so that blue represents low elevations and red represents high elevations. You can see that Venus consists on the surface of island-size and continental-size elevations abutting much lower elevations, which could contain a liquid if it were there. Now, the reason that it's a little warm and the atmosphere is a little heavy on Venus has to do with its planetary history, as I will outline momentarily. We know that this cloud layer consists mostly of carbon dioxide in the upper and lower reaches, and a combination of carbon dioxide and sulfuric acid in the cloud layers themselves. Now, 80% of the light that impinges on the cloud layers is reflected away, but the 20% that gets through is sufficient to heat the substrate to a point where, lacking an ability to escape because of the dense greenhouse effect, it simply warms the air and the substrate up to around 460 degrees centigrade. Now, notice that also the atmosphere is very, very tall, extending up to 70, 75 kilometers. Note, however, if we look at the temperature at these different layers, we find that right at about 50 kilometers up, the temperature gets down below 60, even below 50 degrees. So at around 50 or maybe 52 kilometers in altitude, it's about the temperature of just a warm day in South Texas. The clouds themselves, if we deconstruct them a little bit in this highly diagrammatic slide, this slide represents the three different layers based on size of the water droplets that contain sulfuric acid, up to around 3.5 micrometers in long axis, which are sufficiently large to hold at least microbes, if they are tolerant to the acidity, and the temperature should pose no problem. We have organisms on Earth that live at temperatures well over 50 degrees centigrade. We also know that the chemistry of the clouds consists of sulfur, both in oxidized form and in reduced form. Some carbon compounds also oxidize, and other oxidants and reduced molecules are present along with elemental sulfur. So whenever we have oxidized and reduced compounds together in disequilibrium, we have the potential for energy yielding or energy absorbing oxidation reduction reactions. So if we take this oxidized form of carbon, react it with the reduced form of sulfate, we can generate an organic molecule and elemental sulfur, which in fact can be further oxidized to, with an oxidizing agent to the sulfate that gives rise to the sulfuric acid in the atmosphere, and more importantly, releases enough energy to power the formation of about 8.5 ATP molecules, the high energy compounds that drive intracellular metabolism. So now with this background, knowing what the clouds are like and what the chemistry could be like, let's go back and imagine how life could evolve and where it could end up. So we're going to look at geophysical changes over time, with time becoming more recent in the rising direction. We're going to be looking at two different habitats, life on the surface and life in the clouds. So, early in planetary history, soon after accretion, land masses, lakes, and seas would have stabilized maybe by 4.3 billion years ago, and we could have had the beginning of chemoheterotrophs. There was plenty of chemistry in those ancient seas, giving rise to maybe chemoautotrophs and eventually even to phototrophs, perhaps. Now, as time went on, the humidity would be rising, volcanic activity would be emitting sulfur dioxide, and the rise of CO2 would have brought about global warming. However, for the time being, this was fine. Heterotrophs could have been diversifying, and we could have had a fully functional ecosystem by that time. Now, as time goes on, the sun gets brighter, water gets hotter and more acidic, and the evaporation of water in combination with the rising CO2 leads to a runaway greenhouse. Phototrophs would love it because there's plenty of sunlight, but as the planet became hotter and more acidic, natural selection could have favored the emergence of thermoacidophilic organisms, those that love the heat and thrive in acid. And so we could have had these organisms beginning to form even as the greenhouse gas, runaway greenhouse was getting worse. Now, the phototrophs eventually would have been converted to thermoacidophilic organisms, those who love both the heat and the acid or thrive in it. And at this point, we can imagine that some of them were transferred into the cloud layer. We know this is a natural process on Earth. Our clouds on Earth are chock full of microbes, and so there's no reason why this would not have happened on Venus as well. However, eventually the surface of the planet would have become totally dried out and much too hot for life to persist, so it would have become extinct, but rising in the clouds up to a temperature that is tolerable, and with natural selection promoting adaptation to the acidic conditions, we could have had organisms adapted to those difficult circumstances. And even after catastrophic volcanic eruptions became episodic, creating even more sulfuric acid in the atmosphere, at the 50 kilometers up, we could have life persisting in these clouds. So, Venus doesn't look like a very salubrious place for life to exist, but if we look in the right places, we just might find it. So looks can be deceiving. There is no image of Mars today that we can look at that enables us to imagine a planet that was much warmer and much wetter. But the evidence is overwhelming that that was indeed the case. So if we look at a topological image of Mars, this is color-coded for elevation with blue, dark blue being the lowest elevations, and white being the highest elevations. These are the mid-latitudes of Mars spread out in two dimensions, the South Pole and the North Pole. So the first thing that's obvious is that the northern hemisphere, especially around the poles, is much lower than the southern hemisphere. Also, the southern hemisphere is much more highly cratered, which indicates that impact with the surface was much more frequent. This is exactly the pattern you would expect if these northern elevations were covered with an ocean. And by analogy with geophysical characteristics we're familiar with on Earth, looking for instance at the Hawaiian Islands, what we see for a typical shield volcano is a very gradual inclination down to the shoreline and then a precipitous drop off where water has begun to erode at the pedestal of the volcano. A reconstruction of Mount Olympus on Marche shows exactly the same pattern, suggesting that water at one time in accordance with this artist's conception, was lapping up against the edge of the largest volcano in the solar system and the highest mountain. Now, looking more closely at the surface, we see a typical pattern of a collective network suggestive of runoff gathering into a larger stream and emptying into a basin. We see very wide gorges cut through the surface, indicating very strong, very powerful outflows of water at one time. So let's talk about the planetary history of Mars. This is a bit of a busy slide, but it conveys a lot of important information for us. First of all, this is the timeline in the rightmost column, starting with accretion about 4.5 billion years ago. These are the eons that planetary scientists use to distinguish different phases of geophysical change on Mars. This column shows schematically the amount of inundation, the amount of water that would have been on the surface of Mars. And note that during the Nokian period, Mars was probably recurrently inundated with enough water to cause oceans, or at least seas, which gradually diminished over time, but lasting, withstanding water as late as 500 million years ago. Now, in parallel with this, volcanic activity was also more active during the early part of the planets. There probably is a functional link between volcanic activity and inundations. But for perspective, let's compare that with the planetary history of Earth. Here we see the eons as Earth geologists describe them. We have strong evidence that prokaryotic organisms were existing in the seas of the early Archean between 3.5 and 4 billion years ago. Note that 2.5 billion years ago, eukaryotes, or complex cells with membrane-enclosed nuclei and other intracellular specializations, had evolved on Earth at a time when on Mars there were still significant bodies of water on the surface. Even multicellularity, coming along about 1.5 billion years ago on Earth, would have occurred at a time when there was still some standing water on Mars. So the opportunity for life to evolve in a significant amount of water is very high. There's more evidence for water on Mars today. We might well ask, where did all that water go if there was so much there? Well, it's still there, a lot of it. This is, again, color-coded in the northern part of the planet, near the South Pole. Blue represents a higher concentration of hydrogen atoms, which is the marker for water, beneath the surface. And it diminishes as we move toward the equatorial regions, but it's still found throughout the planet. These rectangles just represent different sampling sites for different things, including imagery for these gullies that appear to flow down the side of cliffs into collection basins. These vary in appearance on a seasonal basis, so we think that these are processes that are happening today. The most likely explanation is probably the expulsion of water from underground aquifers. This is below surface level. Underground aquifers, perhaps during the summertime when the temperature warms up on Mars, can warm up on Mars in the equatorial regions to well into a tolerable range of 15 to 20 degrees centigrade. Just like a pleasant summer afternoon. Another possibility for Mars is the fact that Mars appears to be covered with lava caves. Now, when lava flows out, it cools on the outside first, forming a core around the perimeter. This essentially provides a pipe for the liquid lava to continue to flow. And once that lava has flowed out, then the space left behind is cave-like. And in fact, we see multiple instances of what appear to be collapsed lava caves on Mars. So we have two habitats on Mars: subterranean aquifers, which could handle at least microbial life, and lava caves where even larger forms of life conceivably could be found. Now, please don't try to read all this biobabble here. I just want to make the major point that we're looking at 4 different habitats. First of all, the oceans, lakes, and ponds, which would have been covering the planet. And during the early part of its history, quite a bit of evolution could have been occurring, some of it moving as the planet dried out into subterranean habitats. Eventually, the surface became so dry that not much life could survive there. But it could continue in subterranean habitats, some of them moving into caves and possibly providing a habitat that would handle organisms as large as, let's say, a snail or other grazers that might feed on primary consumers like fungi and moss-like organisms. These, of course, are all pictures from life on Earth, but in terms of order of magnitude and size, they're completely feasible. Even the photosynthesizers may have been present in the early days of Mars. Well, Europa makes everybody's short list of habitats likely to harbor life, if it exists, in the rest of the solar system. Europa is the smallest of the 4 Galilean satellites discovered by Galileo in January of 1610. It is very peculiar in its appearance, very smooth, highly fractured, with evidence of mineral deposits on the surface. These linear crevices running across the surface, indicating fault lines, or what all, we're not sure. But we believe that the interior of Europa looks like this: a metallic core, a mineralized regolith surrounding it, and then on top of that, a layer of water that is global in extent, perhaps as much as 100 kilometers in depth, and a shell of ice on top of the water, perhaps estimated at anywhere between 10 and 60 kilometers thick. Now, to understand why all that fractionation, that fracturing might be going on the surface, recall that the Galilean satellites are moving at different rates around the planet, and sometimes they will be arranged just like this, with Europa, second one out, but at other times they will be arranged like this, with Europa way over here on one side and all the gravitational pull going in the other direction. So the gravitational action difference between this situation and this situation is quite extreme, and we believe is what leads to the type of topography that we can now see on the planet. This is a great close-up showing those fracture lines, which themselves have been separated out. We have big chunks of ice rafting moving about like different pieces of a jigsaw puzzle. So there's plenty of energy inside this planet. Beneath a shell of, let's say, 20 kilometers thick with ice, there is no light, there is total darkness. So we have to think about other sources of energy besides light. Here's one ideal that Dirk and I are fond of. It's one that relies on different tonicity that would exist near the ice ceiling, where melting fresh water would be diluting the salt content, as opposed to the bottom of the water column, where dissolving minerals would be elevating the salinity. And this means that water would be traveling out by osmosis, by diffusion at the bottom of the water column, but be drawn in by osmosis at the top. And if there is a molecular machinery of some type coupled to this movement of water, it could capture the energy of that movement and synthesize high energy compounds. Now, a related concept allows us to move on to a discussion of a potential ecosystem. Let's suppose, as I just indicated, that we have an osmotroph at the top of the ocean, just beneath the ice ceiling, and at the bottom we have an ionotroph, let's say magnesium, which is flowing down its concentration gradient into the cell, both of them coupled to molecular machinery that generates high energy intermediate organic compounds. Well, the rectangles represent schematically the biomass that we might expect based on similar habitats on Earth, where the producers at the top and the bottom are consumed by a primary consumer. The primary consumer then is eaten by a secondary consumer. Everything is dying eventually, providing detritus for detrophores or scavengers to derive even more energy from. So, indeed, it is possible with the appropriate input of energy or harvesting of energy to imagine a fully functional ecosystem on Europa. But it's subsurface, it's in the deep, dark oceans of the planet. There are other bodies like Europa in the solar system. This is Enceladus, a moon of Saturn. Note the rugged terrain up here with a lot of cratering. Note the smooth terrain down here with not much cratering at all, suggesting constantly servicing. And these so-called tiger stripes at the bottom have been observed to emit a spray-like of water and methane. And so there's obviously energy from inside this system. Another interesting body is Ceres, the largest body in the asteroid belt between Mars and Jupiter. Again, a regolith in the center, surrounded by probably water ice, which occasionally results in these cryovolcanic eruptions, which indicate that there is energy inside this body. Okay, moving then to Titan. This is Christian Huygens, who discovered Titan in 1655. This remarkable photograph, taken by an amateur astronomer, shows Dione and Rhea, two of the smaller moons of Saturn, and Titan, all lined up in Saturn's ecliptic, showing proportionally the distance of Titan from Saturn. It's about 20 Saturn diameters away from Saturn. And in 1943, Gerard Kuiper at the McDonald Observatory in West Texas made a startling discovery, and that was when he pointed his spectrometer at Titan, he found unmistakable evidence for methane, the first moon to be shown to have an atmosphere in the solar system. Well, now we've seen more close-up pictures showing the blue haze. The blue haze is due to methane, which reflects blue light. And so the atmosphere is confirmed, and we now have a lot of information about what that atmosphere is like, and it's not simple and straightforward. It is a very high atmosphere, going up to 150 kilometers. It consists primarily of nitrogen, the only other nitrogen-rich atmosphere beyond Earth that we know of in the solar system. These stolons are organic molecules that are produced by reaction, probably interaction with sunlight, with methane and nitrogen and probably ammonia in the upper atmosphere. They form these stolons, which are small organic particles, what we would call on Earth smog. And down at about 75 kilometers, we have a second layer of tholins. And then beneath that, the temperature drops down to minus 195 degrees centigrade. This is too cold for the clouds of ethane and methane to remain in a gaseous state, and they precipitate down, forming the pools of liquid ethane and methane that we think exist on Titan. Now, a lot of this we know about because of arguably the most successful robotic exploration ever undertaken from Earth, the Cassini-Huygens mission to Saturn and Titan. The Cassini orbiter, the main part of the machinery, stayed in orbit while this portion, this encased shield covered a small probe called the Huygens probe, which was sent down to the surface of Titan. Cassini was launched on the 15th of October 1997 after 7 years, which included 2 Earth gravity assists and 1 from Jupiter. It arrived and was inserted into orbit on the 1st of July 2004. On Christmas Eve, the Huygens probe was ejected from the mothership and it spun down toward the surface. When it hit the atmosphere, parachutes deployed, and it made a soft landing on the 24th of January. Once it descended beneath the clouds, we got to see, for the first time ever, what the surface of Titan looked like. Ground-based telescopes had been unable to penetrate that thick, cloudy atmosphere. And the first thing we saw was shown here, a continental landmass-like surface abutting a basin, a smooth-looking basin. And as Huygens descended further, we began to see these really dramatic pictures of channels that are clearly collecting or transporting some type of presumably liquid. I mean, this looks like the Mississippi River and the Arkansas River joining it right here. Of course, this was on Titan though, but it looked very much like features that we're familiar with on Earth. Dark chasms here, and then some very dark areas which are radar signals, most likely for liquid. We see continental masses of dark areas, again suggesting a lot of liquid, and now more recently, or not recently, but soon after Huygens came to rest on Titan, more measurements from Cassini revealed, especially in the polar regions, multiple bodies apparently liquid, and some of them are quite big. So for perspective, this one on Titan was about the size of Lake Superior. So these are not trivial collections of liquid. We think the interior of Titan then consists again of a metallic core. High pressure ices enclose that core, and there appears to be, there's good evidence that there is liquid water, probably as a liquid ammonia mixture, then overlain by a layer of ice and water ice and probably frozen organic molecules and other small molecules, and then the very dense atmosphere that we've already talked about. This is an artist's conception of what a rainy day on Titan might look like. The rain, though, being methane and ethane primarily. So the way Dirk and I envision this is that there are really two habitats or two compartments we're concerned about on Titan. An ammonia water habitat beneath the surface, which could remain liquid because of the high solute content and the high pressure that would be on top of this water pool. Now, the surface is much too cold for water, no matter what its solute content, to exist in a liquid phase, but ethane and methane and other organics could well exist in the pools of what is essentially like gasoline on the surface. Occasionally there will be eruptions, cryovolcanic eruptions that will return the ammonia and the methane to the atmosphere, because one of the curiosities about Titan is that ammonia and methane remain in the atmosphere much longer than on theory they should. So probably that atmosphere is being recharged. Well, what do we do with this information in terms of imagining a trajectory for evolution under such exotic conditions, at least exotic by Earth standards? So again, as usual, we begin at the beginning with the accretion of rock, water, and volatile gases at that distance from the sun. This gave rise to a methane and ammonia-rich atmosphere close to 4.5 billion years ago. But it would have been warmer then, and so there may have been water, which would have provided a habitat for chemoheterotrophs to start their evolutionary life, as they generally do, or as we think they have. When the conditions are right. They did, after all, within that time frame on Earth, and so there's no reason why, under similar conditions, it wouldn't have happened on other planets. But the conditions on those other planets changed, so a massive atmosphere of methane and ammonia would have covered the global ocean. It would have been liquid in the beginning, but eventually it would have become too cold to keep water liquid. In the meantime, though, some methanogens, these are microbes that metabolize, that oxidize carbon dioxide and other organic compounds into methane. Other chemotrophs could have evolved, and where there is life, there is death, and detrivores would have come along pretty soon. So, as evolution continued then, continued as the global ocean would have frozen over, if it had existed, it would have frozen over, but kept liquid beneath the surface by all this dissolved ammonia. Meanwhile, but of course it would have been very alkaline because of the ammonia. So in the meantime, we could have had evolution of, let's say, substrate biofilms. We could have had alkalophilic heterotrophs. These are heterotrophs that natural selection has favored an adaptation to highly alkaline conditions. With continued cooling, ethane and methane rain began to fall, scouring the surface, as we've seen before. And in the beginning, alkalophilic heterotrophs, again, heterotrophs adapted to highly alkaline conditions, would have evolved or may have evolved into a more hydrocarbon tolerant point to where they could actually cross over into now a new habitat on Titan, which I'll call the lithosphere. Ancestral hydrophobes could have evolved, and then as conditions became really drastic on the surface, we could have had in those subterranean aquatic environments still more evolution, and in the lithosphere evolution as well in a different direction, so that even today we could have some complex organisms swimming around in the liquid ammonia water habitats beneath the surface, and perhaps more complicated organisms living in the hydrocarbon environment. The latter is possible, as indicated by the fact that on Earth we have this organism, Fusarium alkalinophyllum, which is anaerobic, and it grows in saturated hydrocarbons and UV light, just the type of environment that an organism might enjoy on the surface of Titan. Now, if you're wondering what this organism is, don't ask me. I don't know, but it appeared in a peer-reviewed publication describing Fusarium, so I take the author's word for it that it is indeed a fungus-like organism that likes to live in something akin to gasoline. Well, let me summarize then by saying that if we're looking for life, we just need to look in the right places. That means suspended animation in the clouds of Venus. It could mean beneath the cold, dry desert of Mars, and possibly in her caves. In the deep, dark depths of ocean worlds like Europa, and in the exotic subterranean aquifers, and the lithosphere of petrolakes and seas on the surface of Titan. I'd like to end this with this quote from Johannes Kepler. He wrote at the turn of the 17th century, "When ships to sail the void between the stars have been built, there will step forth men to sail these ships." And indeed, we have, sending men to the moon, 1969, sending the first experimental probe for life on another planet, with the Viking landers in 1976, the fabulous Voyagers, both of which have now passed the heliophase and therefore beyond the reach of our solar system into deep outer space. The International Space Station, which on 30th of October, when a new crew arrived, marked the last day in the history of our planet when there was not a human continuously in space. Then, of course, we have our rovers on Mars, and then this solid bowl-sized probe, long since silent on the surface of Titan, but giving new testimony long after we've passed from existence that there was, at one time, a race of beings bold enough and curious enough to send ships sailing among the stars. Thank you very much.
All right, any questions?
Yeah. Could you go back to the second slide that had your two books on? I'll get a picture of the two books so I can look them up.
The seventh slide after what?
Well, I think it's the
The
second
second slide, your
Had
books.
Your two books.
Oh.
We can get a little promotion here too.
Yeah. There we go.
So again, if you want more detail on this presentation, they're out there on Amazon, etc. Any other questions? Mr. Bailey?
Yeah, question about two time scales. One is any estimate of how long the runaway greenhouse gas on warming on Venus took to take place? And the other one is on Venus also, how quickly would downdrafts bring organisms down into hot regions and kill them?
So basically, how long did it take for the runaway greenhouse effect to kill life on the surface of Venus, and how frequently would downdrafts bring life back down to the surface and potentially replenish the atmosphere and maybe extinct things in the atmosphere?
Thank you. I don't know how long, and I'm not sure that anyone knows how long it took for the runaway greenhouse gas to appear on Venus. It was probably fairly early. If I had to guess, I would say it was probably fairly early on, but probably not before 1 or 2 billion years, so plenty of time for life to form. As far as downdrafts of the clouds, we know the circulation pattern of the clouds on Venus, first of all, are very high, and we know that the droplets last for weeks, unlike clouds on Earth where they last for a matter of days. So I really don't know how much downdraft there would be, but it would be expected to be less. I would expect it to be less than on Earth.
We know the Russian Vega probes actually traversed about a third of the atmosphere of Venus before they went silent, and they may have stayed up in the atmosphere much longer. So.
Another one. Is there any known microorganism that lives in the Earth's atmosphere?
Are there any known microorganisms that live in the Earth's atmosphere?
Oh, yes. Yes. Well, the clouds are chock full of microbes, of many different taxa. They are all microbes. I mean, we don't know of any, permanently dwelling organisms that live, that never come down to the ground. And we also don't know to what extent they are on Earth, in Earth clouds, they are able to reproduce, but there's no reason that they couldn't, that the bacterial forms couldn't reproduce by fission. But I don't know of anyone who's actually documented how long a single microorganism stays in the clouds. We just know that they're up there and there are a lot of them, and so there's no reason to assume that they wouldn't be on Venus where temperatures would allow it if they are sufficiently adapted to the acidity.
Dr. Parker?
In terms of the possibility of life in the atmosphere of Titan, it's really cold. Most chemical reactions are thermally activated, which might suggest that chemistry would be extremely slow there. Is that consistent with life in the atmosphere of Titan?
Is the atmosphere of Titan conducive to life? I don't think so, because the temperatures are way too cold. At every altitude, they're just too cold for any any water-based liquid to be liquid. It would have to be a truly exotic form of life using, using probably ethane or formaldehyde or something like that, which is theoretically possible, but it seems unlikely. I think there's much higher probability that it will be on the surface in the petrolakes or beneath the surface in the water ammonia habitat.
Ms. White, you had a question?
Yes, where do you think we might look next?
Where should we look next? Where should we send a probe next to, where should we concentrate our efforts to find life on other worlds?
Where we should send a probe is to the clouds of Venus, because it's close, it's downhill gravitationally from Earth. We have the technology for collecting particles from the atmosphere and returning them to Earth. It's been done. Realistically, where will we in fact look? I'm sure it will be Mars. We will send we will send humans to Mars to look in detail, if we don't discover life already, just through our robotic probes that are already really looking pretty closely. Ultimately, the most interesting would probably be a mission to Europa.
Jerry?
Have you looked at any of the exoplanet data? In a
Any,
similar way that you've done with the moons?
Can we get any details about exoplanets that would give us the sort of ideas that we have looked at for our solar system?
Thank you. That's a great question, and the answer is we just don't have enough information on exoplanets. As we heard from the previous speaker, there are exoplanets that are vaguely like Earth, and with red dwarfs and different spectral characteristics and different distances from the central star where temperatures could be appropriate, do exist, but the thing that we're most lacking is good chemical information on what chemistry exists on those planets. We know what's in the stars, but the planets are just too small. We don't have the technology yet to get that type of information.
Dr. Martin?
Not too long ago, we thought all life on Earth had to be kind of like us, okay? And then we came across a whole bunch of organisms that are called extremophiles. In fact, I worked on the structure of a couple of enzymes that are happy to live at 95 degrees centigrade. And we started getting cameras down into the ocean where they don't even use oxygen. They use hydrogen sulfide as the redox components to live. You get tube worms and all kinds of things. I would think it's almost impossible not to find life of some kind on one of our planets.
Well, I'm basically with you on that. I don't know if I would go so far as to say almost impossible, but certainly one of the messages in both of our books is that we need to be open-minded about what constituents and conditions life can in fact be found in, and the examples that I gave for all of the planets require extremophiles. In Venus, the extremophile would be acidophiles. On Mars, psychrophiles, which give a shout out to my wife who worked on those extremophiles in her graduate studies. And then obviously on Titan we're talking about cellular constructions and processes that if they are not based with water or just so unfamiliar to us, we might not even recognize them. But that doesn't mean that they couldn't form the types of complex systems that I have defined as a living organism.
All right, one last question right here.
So how large is the danger that if we send probes to look for this life, those probes will carry Earth organisms which can then contaminate the environments we're looking in and give us some kind of false signal?
So how great is the risk that when we send probes to the surfaces of these places, when we drill into Enceladus, how are we going to avoid contaminating them with Earth life, and how are we going to be able to distinguish Earth life from the life on these other worlds?
If we know what life looks like on Earth, and if we find organisms that are very different from that, then we can conclude, I think, that they're different. If they're not different, then that raises the interesting possibility that all forms of life in our solar system have either a common origin, which seems highly unlikely, or have generic constraints that allow only carbon-based, water-based forms of life based on protein, lipid, hydrocarbon, nucleic acid biochemistry that we're familiar with. Also seems unlikely. I think the chance of contamination, which is a real issue in the astrobiological community for sure, Dirk and I'll get him to share some of the blame for this. We downplay that possibility somewhat because Earth organisms have evolved in just such very different conditions that their ability to survive on a very different planetary habitat would be low in our opinion. But it still is a concern that we can't discuss.
All right, well, thank you so much.